Hello, and welcome to our first lecture on Introduction to Experimentation and Active Learning. This is the first lecture of a two-part series on these topics, and in this lecture we intend to motivate the use of these techniques as well as the concept of reinforcement learning. So the reinforcement learning is a separate lecture that you will have, lectures that you will have from Professor Ravindran. And in this lecture, we will motivate the need for these topics: experimentation, active learning, reinforcement learning. Why are we talking about them in a data analytics course? And we will also briefly introduce the topic of experimentation or design of experiments. And in the next lecture, we will continue with experimentation and end with active learning. So let's get into the subject where we where we take a broader look at data science and analytics, right? The core idea is that data science and analytics need data. And if we were to go with the big buzzwords now, we might even need big data, where we can really gain useful insights. And this is quite fairly motivated with the easy availability of storage, the easy availability to process data, and the Internet of Things generating a lot of data. It's quite easy to get troves of data and analyze this data and come up with useful insights. But in not every situation do you start with a database full of data. And in not every situation is it easy to create this data. It might either be costly, or it might not be. The data that you might have is not the relevant data that you need. And in many cases, you just haven't started the exercise. So for all those cases, the big question is, do you have no scope for data analytics? And the answer really is that there is this whole other set of tools and techniques, the quantitative tools and techniques, which focus really on not just the analysis part of data, but have something to say about what data gets created, which then goes and gets analyzed. And that is the focus of these lectures on experimentation, active learning, and reinforcement learning, which is that data science is not confined, or data analytics is not confined to troves of data that are already available, but it's more of an interactive, iterative process where sometimes the question of creating the data is also intrinsically looped into this grander problem statement. Now, sometimes we won't even give a second thought to this dichotomy of creating data and analyzing data, right? Because some problems just inherently come with this creation. So if you take a look at many of the inferential statistics techniques that we saw earlier in this course, right? Let's take an example where we used a two-sample t-test. You essentially had to sample n number from data from class A and class B, so and compare the means. This whole process of sampling was in some sense creating the data. So let me give you a concrete example. One of our favorite examples might have been that our 10 standard girls, is the average height of 10 standard girls higher than the average height of 10 standard boys? And there we said, we need to go take a sample of 10 standard girls and a sample of 10 standard boys. And we came up with the conclusion that, and we did a hypothesis test there. So when you do a sample, you're essentially creating the data, right? And in other situations as well, where you were doing some kind of an engineering experiment, perhaps, and somewhere we didn't really use the word experiment excessively, but the idea is that sometimes we never thought about it. But those are fairly the simpler cases. There are a lot more cases where you need to explicitly think through the creation of the data before any kind of analysis can take place, and that's what we will focus on in this lecture. Okay. Now, when we speak about creating data, a very important factor becomes whether this is an online context or an offline context for creating the data. Okay, what do we mean by that? Online and offline online does not mean that you're on the internet. It means something different here. What it means is essentially when you're in an online setting, That means you are experimenting or you are creating data on a system, right, that is currently creating a product or producing or involved in performing a service or a task, which is going to the end user. And for the purpose of getting this data, you are not just starting a passive observation exercise, right? So you are actually either querying the system or you're either playing with the system in order to get the data that you need. Now that can be a problem sometimes, right? That can be a problem sometimes because you are actively interfering with the system to create the data that you need. And this system is right now either producing a product that's going to the end user, or this system is a live system which could influence the experience an end user is having. And I'm using the word end user in a fairly broad way. If you experimented on a traffic signal, the end user are the motorists who need to go through the traffic signal. If you play around with a manufacturing process which is producing a product, the end user is the ultimate user of the product that goes and reaches the customer. If it's a process, then again the process itself has some outcomes, right? It either gives the end user some information, or the process itself performs a task for the end user, and all of these things could be getting compromised if you're playing with the live system. And so a major area that we would be looking at is the one of reinforcement learning, where where you're looking at an online system. So you care about learning, where you care about this learning in a very supervised learning framework, where you have some outputs and you want to understand how these inputs affect the output. That's one side of the story. But there's a second side of the story, which is you don't want to you are interested in doing as well as you can even while you're experimenting, because some consumer or end user is experiencing the effects of your experiment, and you yourself could be the experimenter, could also be the consumer. So we're not we're going a little abstract out here. So but the advantage of going this abstract is that you can really envision any scenario in any domain, and this kind of a framework should apply there. So we will see that primarily the online setting, or I'd like to kind of call it the live setting, live experimenting, gets covered in reinforcement learning, and those lectures will support that. Now, in going forward, now in this lecture and the next one, we are primarily going to talk about an offline setting. What do we mean by an offline setting? Just the opposite of the online, which means that the unit that we're experimenting on is not producing products that are going to go to the end user. So you've either created, and you can do this in many ways, right? So if you want to conduct an experiment and you want to gather data, you can create a model of your system and go experiment on that model. Right? You can artificially create a lab setting. Let's say I wanted to experiment on what fertilizers worked on my fields. I don't have to go pour those fertilizers on my fields. I can actually create a greenhouse and choose some specific plants and try these fertilizers out, and I can essentially create this lab setting which is supposed to mimic the real world. But it's not always creating models. I mean, it could be creating models. It could be creating artificial environments. It could be creating computer simulations, and then you go experiment on that. But it can also be the real process, except now you've turned off the real process. So let me give you an example. Let's say you wanted to do an experiment on a machine. And this is a machine that's used in manufacturing, and you wanted to know how to set various boilerplate stuff on this machine. So you wanted to know what the speed should be, what the turning radius should be, different parameters associated with this machine. Now, if the machine is currently manufacturing the product which is going to the end user, that's a problem. But what if you stopped the entire manufacturing process, and you said, we are going to now exclusively commit some resources to experimentation, so we learn about the system. And so you play around with the machine, play around with various settings in the machine, make it, create products, and then you measure the products and see how well you did or how badly you did, and you learn about the system. So you created the data, you analyzed the data, you learned about the system. But these products that are sacrificed in some sense, they're not going to the end user. In other words, you don't care how well you do when you are experimenting, and that's the core of offline experimentation. A bad experiment is not one that gives you poor results, but a bad experiment is one where you cannot learn about the system. Your focus is about creating data to learn about the system, and that does not mean there is no cost to experimenting. Right? There is a cost, but you can think of it as a fixed budget that's been sacrificed, or you can think of it as there being no cost at all. However you want, but it's not that while you're experimenting you're trying to perform as well as possible. That would be the online setting. Okay, so now that we've understood this difference, it's also important to understand the difference between observational data and offline experimental data. And I use the word in DOE. So we've for the first time we started using the word DOE. And here we mean design of experiments. It's a more formal way of talking about experimentation, of talking about statistical experimentation. And the idea here with this difference between observational data and offline experimental data is the fact that with observational data you're not interfering with the system. So let's go back to the original problem. We said, hey, how do you do data analytics when you don't have data? Okay, one approach is to say, okay, so I need to start collecting the data, and so perhaps I'll turn on a few sensors, or I'll put some sensors in certain places, and I'll start collecting the data. Now that in itself is not the subject we're talking about here, right? That's just turning on the switch of collecting data, and once you have the data you analyze the data, and that's fair game. That's data analytics in some sense, but that's data analytics that's coming from observational data. Okay, what we're focusing on right now is there some way for me as the agent that wants to collect the data to actively engage with the system and choose what data gets collected? And that's what we will be doing both in design of experiments and active learning. You are in an offline setting, meaning that you are right now committing all your resources to collecting the data, and you can collect whatever data you want, but the point is that you are going to be controlling what data gets collected. And as a result, the only way to do that is not to passively observe the data that gets generated, but to actively, in the case of design of experiments, you will actively go and change some of the settings in a system, or very specifically go query certain points, and that's how the data gets generated. A typical problem statement in experimentation would actually say, go set the machine to setting A and setting B and setting C, and then let's see what the output is. And in active learning is seen a little bit more as that entire data, the input space is available, and you get to query a particular point in the input space and then get the answer. Now these are just two different ways of describing it because they come from slightly different contexts of application, but the core problem statement is the same, which is that you as the user and experimenter or learner has the choice of generating an output at a pre-decided point in the input space. And that has some critical difference over observational data and a lot of advantages. Just to give you some intuition, the biggest advantage is one concerning multicollinearity. If you were just to observe the data, it's possible that two input variables are so highly correlated to the point where there's almost a perfect correlation, in which case you would never know if the output was increasing or decreasing as a result of input variable A or input variable B, because input variable A and B are so highly correlated. So in the case of design of experiments or active learning, you would come to that realization at some point without passively observing data and say, oh, we need to try out an experiment, or we need to query a point where input variable A is high and input variable B is low. and vice versa to try and understand which of these two input variables is having an impact on the output. Okay, so let's start with focusing our first lessons on experimentation and design of experiment. The core idea with design of experiments is that as long as you can conceptualize the operation of a system as some combination of inputs, which when used together result in outputs, you have the scope for this kind of black box creation, and a black box, essentially an understanding of the way the inputs and the outputs relate to each other. So the inputs themselves can be anything, they can be really broad. The only important thing is you want to be able to quantify them in some way. The black box that you're experimenting on can be anything. It can be a process, it can be a system, it can be an organization which is performing certain organizational functions, it can be an actual product, right? And typically, what are the outputs you're interested in? The result of this black box could be that some products are being created, and you can measure these products and therefore measure how good or bad they are. The output could be some services or tasks that are created by this black box, and again, you should be able to evaluate the output. And the third is a little bit more abstract, which is some information is getting created. Again, as long as you can quantify these outputs and quantify the inputs, you have a system whereby there is scope for experimentation. So formal experimentation, what is it, and how is it different from just observing data and analyzing it? Formal experimentation essentially involves systematic, that's a very important word, systematic and purposeful changes that you make to input variables in an attempt to gain knowledge about the system and or find the ideal settings that result in the best output. So that sentence is a little long-winded, but let's kind of break it down, right? So the idea is that in experimentation, you proactively go and systematically or purposefully change the input variables. Okay, it would mean that you actually go and say, oh, I need to understand a little bit about the system, so I'm going to try setting input variable A to a particular value, input variable B to another value, and then I'm going to go look at what output I get. Okay, and the purpose of this, now in some rare cases it could just be that you are not physically changing the input variable, but you're physically choosing the input variable that you want to observe, right? Because you don't have the information about how the output is going to look at every point in the input space, so you are not making a modification to the system. There exists this large enough repository of information which is very expensive to query, because if it's not, all you have is a huge data set which requires a supervised learning task, right? But for some reason, if this is very expensive to query, you could also think of experimentation in light of choosing very carefully the input variables that you want to gain knowledge about. But more often than not, the typical context is that you have this system where you go actually change the input variables, set them to different values. So think of this, perhaps this foundry process where you're trying to create casts, and your input variable could easily be the temperature of the molten metal that you're pouring in, the pressure that is being applied, the kind of material that the cast is made of, and your output could be the number of defects that you see in the cast, right? Now, in an experimental process, you would go and systematically, purposefully try different temperatures, different pressures, different materials to make the cast, different practices in the cast. How long do you wait before you open out the cast, right? What kind of a room do you place it? You would go actually physically change these settings to different values and observe what happens to the output, which in this case is the number of defects you see. So the emphasis here is in the systematic and purposeful changes to the input variables. Now, why do you do it? You could do it for two reasons. You could do it to gain knowledge, right? And you could do it to find those settings that you want to set the inputs to get the best output. Now, the gaining knowledge could just be an independent process. That could be the final goal. Sometimes the approach is to gain knowledge, and once you've gained the knowledge, And what knowledge are we talking about here? We're talking about the knowledge associated with how the input variables affect the output variables. Now, you could then, once you've gained this knowledge, use that information to figure out what are the ideal settings for the inputs. But you also have algorithms which say, you know what, I don't care about the knowledge. My goal is to right now find out what those settings should be so that I get the best output. And that takes on a different form. Okay, so that's the core idea of experimentation. So at this point, a very natural question arises. Okay, so you've got some 2 or 3 or 4 input variables, and you've got an output variable. Okay, what's the problem? Why don't we just play around with each input variable, one at a time, and see what's the best setting for each input variable, and do this sequentially, right? Turns out it's not that simple. Okay, there's a simple problem with that, and I'm going to try and illustrate that with this diagram. Okay, let's say that this plot that you have has 2 input variables. Input variable 1 called x1 and input variable 2 called x2, and the output is nothing but a hill that is projecting out of the screen, and this hill is shown with a contour plot. A contour plot basically is one which connects, which is often seen in maps, where you basically draw a line where the height above sea level usually is the same. So here, imagine that there's this flat surface, which is the base, the rectangle, and then there's this hill projecting out of this flat surface, out of the screen, and coming towards your face, as if you're looking at the screen. And these ellipses that you see on the screen, these kind of circular looking things, are nothing but the contour plots. So that means everything that is on this line is 70 meters or feet or inches, whatever you choose to think of it. So this is an example of a response surface. I've basically tried to characterize in this picture how the variables x1 and x2 have an influence on the output y, which is the hill coming out of the screen. So it's an abstract concept. Okay, now let's take a look at what happens when you just play with one variable at a time, and we're going to call that adaptive one factor at a time experimentation. The idea behind this algorithm is that what I'm going to do is at any given point of time I'm going to play with any one variable. So I'm going to start with, let's say, x1, and I'm going to try different values of x1, and I'm going to make a conclusion at some point by saying at what value of x1 did I see the best y, and I'm going to go with that. I'm going to fix x1 now to that value and play with x2, and I'll sequentially do that with all the input variables until I come to a conclusion. Now take this example where I start playing around with x1 and I arbitrarily fix some value for x2, and it turns out that I fixed the value right here. Okay, so we'll put a star there. Okay, so I started with x2 set to this value, and I just started playing with x1. So what does it mean when you play with x1? That means you keep changing x1, and here you're actually just changing x1 to different values, and as you go through different values, you see different heights. For instance, when you set x1 to this value, you're seeing a height of 70. Why? Because this is the contour line of 70. When x1 is equal to this value, you see a height of 80. And so you keep going through this process and until you find the highest point. And the highest point is here, right? Because at this point you're touching 80. For instance, at this point, right, at x1 you were not touching 80. You were between, it's somewhere close to 75. So you conclude that this is the best value of x1, and then you set x1 to this value. Okay, so x1 gets set to this value, and then you go about changing x2. Okay, and basically when you're changing x2, you're staying on this gray line out here, and as you keep going through x2, you find that the point where there's a star is the peak, and you conclude that that's the highest point. So you choose to set x1 and x2 such that you are at star. Okay, clearly, what's the problem with this? The problem is that you miss the peak. Okay, there are two problems in this. One is that you missed the peak. The peak was really out here. If you take a look at this contour map and you understand the contour plot, the plus sign is where the peak is, and you erroneously concluded that the star is where the peak is. And the reason for it is fairly simple. The way this hill is drawn, it's clear that x1 and x2 have some interaction effects, right? That is, x1 is really good out here because when x2 is set to this value. Now, if you set x2 to another value, right? Like let's say you set x2 here, the highest point of x1 is probably somewhere here. So this value of x1, right, winds up being highest. So it really, what we mean by an interaction is where you conclude x1 to get the best output depends on where you set x2 to, right? So there's this interactive effect that you can sometimes get fooled by. There's another thing that we've not really discussed here, which is that if you do an experiment at a given x1 and x2 setting, are you always going to get the exact same value? And the answer is probably not, right? Experimentation is typically carried out in a stochastic setting, meaning that even if you understand that your output y is some function of your input variables. In this case, there are two input variables. So there's some mathematical function that's associated with input variables x1 and x2 and the output variable y. But on top of that, if you set x1 and x2 to two specific values, are you going to get the same y? The answer is, in a stochastic system, you don't, because there's an other factor which is just, you can call it noise, you can call it irreducible error, you can call that luck, whatever it is. It's this concept of just there being uncertainty above and beyond your, and this kind of uncertainty is what we deal with in supervised learning. It's what we deal with in much of what we've discussed in this course. So that aspect also can throw you off in an approach like this. Now, this has been illustrated to you in a continuous framework where you were able to change x1 continuously and see different. But in a more practical settings, you don't have infinite experiments. So you might just set x2 to a particular value and sample x1 at some 1, 2, or 3 predetermined values. More often than not, in design of experiments, you will see that we are only interested in linear effects. Most of the cases, you're interested in linear effects. So you would really look at trying out each variables at two different points, because with 2 points you can draw a straight line, and the 2 points typically get coded. So what's another approach that you can do, that you can employ to overcome this problem? The other approach you can do to overcome this problem, and one of them is broadly called as orthogonal arrays, and a specific type of an orthogonal array is called the full factorial, which is what I show here. So take a system where variable a can take on two states, right? So let's go back to this casting problem, and let's say you were interested in variable a, which is let's say the temperature of the molten metal that's poured in. And so the temperature could be something like 250 Fahrenheit, and you might be interested in studying the effects at 350 Fahrenheit. Now I'm not an expert in this, so I don't know if those are reasonable temperatures for molten metal. I'm guessing it's a little too low actually, but who knows. Now typically what you do is, when you have just these two settings, you kind of code them, and you call them 250 as -1 and 350 as +1. Now you do the same thing with the second variable, input variable of interest. Now variable b could be something like pressure, right, where you have low, or let's say the time that you wait before you remove the cast. So that could be 1 hour or 2 hours. Again, I don't know if those are reasonable numbers. They're to illustrate a point. Okay, so 1 hour, again you call it -1, in 2 hours you call it +1. So what you go about doing in a full factorial is you try every combination of every variable with every other variable. So you try the -1 setting, okay? You try the -1 plus 1 setting, so +1 -1 setting, and you get the picture, right? You essentially try every possible combination, and that's called a complete enumeration of the design space, because you have discrete data points, and you might choose to do some experiments at each of these combinations of points. Okay. In this example, I've shown you two replicates. These are called replicates, and these are both the same output variable y, but you choose to take two readings, right? It's actually unfair to call it two readings, because it's not like you do the experiment just once and you just use the same measuring device and just take two readings. You actually redo the experiment. Okay, and the reason you do that is because of the concept we just discussed, which is you acknowledge that your y is some function of, in this case, variables a and b, but on top of that there's some error. Okay, this error often is thought of as being Gaussian with mean 0 and standard deviation equal to some value. But even without going into that, there's just some noise, and you can see that, right? Even though you set a to -1 and b to -1, first time around you got 57, second time around you got 56, and you'll see different levels of uncertainty. Now the same concept extended to three variables is what's shown here, right, on the right hand side, and you have a, b, c, three variables. And I'm also showing you a case where you're not just interested in two levels, but you might be interested in three levels. So variable a has three levels, variable b has two levels, and variable c has two levels. So a complete enumeration of them would be nothing different than 3 times 2 times 2, which is equal to 12. And we call the 12 treatment combination. So you have 12 rows out here. And again, here I'm choosing to take two replicates, just to get a better idea of the noise that is there in the system as well. But the hope is that taking on such an approach would enable us to perform a form of analysis on the data, which helps us understand, which helps us not get tricked by this Gaussian, this noise that's there on the system, which can make you conclude the wrong things if you were not aware of it. And at the same time also understand that there can be some interactive effects between A and B, or A and C, or B and C, right? And that's what we will be focusing on. So in this part we have focused a little bit more on how the experiments are itself designed, and this is just one way of designing experiments, and this is called the full factorial design. And there are other ways of doing the same thing. In the next lecture, we'll briefly talk about how do you analyze the data that you get from such an experiment, and we will also be talking about active learning. Thank you.